Okay, so here's an example he didn't give, but I think it's also very interesting. In geometry, when we have a right triangle, we have something called the Pythagorean theorem.
Yep.
That tells us that the length of this side squared plus the length of this side squared equals the length of that side squared. Okay. And so, do you know an example of a Pythagorean triangle?
There's 3, 4, 5.
Okay, so there's a 3, 4, 5. Do you know an example of one that's different?
7, 24, 25.
There's a 7, 24, 25. Okay, great. I'm going to show you that one of the legs, if I have integers that solve this equation, one of the legs has to be a multiple of 3.
Alright.
Do you know any other examples?
Well, we have 5, 12, 13.
Do you have a multiple of 3 leg?
Yeah.
You have this 12.
We're going to look at a clock with 3 multiples. Okay? So
a
0, 1, and 2.
clock.
So a base 3 clock. And we're going to look at the squares. What does 0 times 0 equal on this clock?
It's 0.
You start at 0 and you go 0.
And what about 1 times 1?
1 times 1, you go, it's just 1, 1. So 1.
1. Okay. What about 2 times 2?
2 times 2.
Well, you start at the 0. 1, 2, 1, 2. So you get a 1.
Okay. And so if I look at base 3, all of the numbers, or if I look at any of the integers, they're always going to be either divisible by 3, have a remainder 1 when you divide by 3, or a remainder 2 when you divide by 3. So what this tells us is that all the square numbers are either divisible by 3. When is that going to happen? When is the square going to be divisible by 3?
When the integers that make the square are divisible by 3.
Or they're going to have a remainder 1 when you divide by 3. Okay, so 4 has a remainder 1. 25.
As a remainder.
49, because 48 is divisible by 3.
Yeah.
11 squared is what?
11 squared is 121.
Is that one more?
120 is.
Okay.
Cool.
Yeah.
So now I just look at the squares. So I could have, so here's my Pythagorean theorem. I could have a multiple of 3 plus a non-multiple of 3, which would end in a 1, base 3, equal another number, base 3, right?
Yeah.
Or I could have where they're all multiples of 3.
And then that would equal a number that would be a
Can you figure out a right triangle that has all the sides that are multiples of 3?
Well,
Well, 0, 0, 0.
No, not really a triangle.
Yeah.
I could just multiply this one by 3.
Yeah.
9, 12, 15, for example.
and
They're all
then
multiples of
if you
3.
multiply those, you can.
Yeah. But can I have it where they're all not multiples of 3?
Well, then you'd have to have. Well, then you'd have to have a 1, a 1,
1 plus 1 would have to equal,
a 2.
it would have to equal 2
But
by
you
our
don't
clock
have a 2
arithmetic.
here.
But this has to be a square of an integer, which is 1. So we would have to have 1 plus 1 equals 1.
That doesn't work.
Nope.
So you have to have a multiple of 3. Isn't that interesting?
Yeah.
Do you notice any other multiple that you seem to always have to have
Well,
based on R3?
looks like a multiple of 5.
Yeah, does it have to be on the legs?
No, because you have one on the hypotenuse here.
Huh.
And then
Another one on the hypotenuse.
So the multiples of 5 can be anywhere.
But it looks like you have to have a multiple of 5.
Yeah.
Huh, I wonder why.
And maybe it looks like.
What clock do you think would help us?
Well, a base 5 clock.
What were you going to say? Sorry, I didn't mean to interrupt you.
It looks like maybe you have a prime there, here, and here's another prime, and then there's at least one prime there.
Oh, very good thing to wonder. Do Pythagorean triples where you haven't multiplied by 3 or something, where they have nothing in common,
Yeah.
do you have to have a prime?
Well, we don't really have any clocks to help us.
Yeah, see, now that's a very interesting question. I wonder if clocks could help us on that or not.
Well, but primes are infinite, and then the primes differ.
So an infinitely long clock.
That's a very good question to ask. The question you asked. That's a very good question. We'll have to wonder about that.
Yeah.
Okay? Alright, so one last thing real quick.